Now, in the previous lecture, in the second series of lectures, we talked about the random experiment. First of all, we had a random experiment, and which the outcomes are not totally deterministic. There may be multiple outcomes, and depending on the nature of the outcomes, whether they are countable or whether they are finite or countably finite, we call them discretes, the random outcomes, or whether if they are infinite, we call the outcomes continuous. And then we talked about the sample space, the all possible outcomes. And then we talked about event spaces, which are the ones that we are interested in. So there was basically a picture of a typical random experiment. How we can conceptualize a random experiment. And then we talked about what the probability may be, or different interpretations of probability, axioms of probability at some rules, which are actually easier to understand, especially in discrete outcomes, as I'm going to talk about today. So now let's go one step further and define random variables, and let's complete the whole picture. So random variable is simply a function that assigns a real number to each outcome. Actually, it's a function, but we do not think it as a function. Therefore, we call it not a random function, but we call it a random variable. The idea is very simple. If, for instance, you toss a coin, your sample space is actually, toss a coin once, that's the important point. Your sample space is head or tails, right? Two different outcomes is possible. So what the random variable here means is, so that's actually one step further from the lecture 2. We assign each value here, each different outcome to a value. So for instance, here the random variable takes the name title X, for instance, and the outcomes of that random variable now turns into 0 and 1. So here, for instance, head is going to be 0 and tails is going to be 1. You can assign any value. Of course, heads could have been also equal to 1. So of course, if the outcome is directly numerical, that's actually easier. But you can assign any real value. That's an important point. If you like, you can assign X is equal to 0.05 to tails and 1.73 to heads. That would be pretty much nonsense, I guess, but still you can do that. And another important point, sample space now has turned into a random variable. And we usually show the random variables, the name of the random variables, with an uppercase letter. And usually we show a lowercase letter of the same letter, lowercase form of the same letter, to denote a specific value of that random variable. Now that may seem a little bit confusing, so that's why I'm not, although in examples in your textbook, we are going to be careful with that notation. I don't expect you to be that much careful about that point, but just know that that is the usual convention. All right, so here there may be other examples. If you roll a dice, the sample space is already equal to 1 to 6 discrete values. So it is easier to think of, although you can assign any value to each of these outcomes, usually it is more natural to think about the random variable as taking these separate values. Now, one important point here is if you, for instance, toss a dice twice, then the sample space is going to be head, tails, tails, head, 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 and tails, tails. Now that's an important point. Now the sample space, each of these elements is going to be an outcome from the sample space. Now in this case, we define X, and we are going to give each value, each outcome a different value. For instance, this may be equal to 1, this may be equal to 2, 3, and this one may be 4. So as you can see, you do not separate heads and tails within one outcome, because this whole series, heads and tails, is an outcome itself. So each of that x is going to be another value of the random variable that it takes, and the random variable is going to be that heads and tails. Now, an important point that we have talked about previously in terms of outcomes and in terms of random variables is the same thing, because actually outcomes are mapped into real numbers in random variables. A random variable may be continuous or may be discrete. So if the random variable takes on a finite or countably infinite distinct values, right, then that random variable is going to be discrete. Actually, I'm going to prepare a short bonus video, slightly more technical, but to sum all of these up, especially those finite and countably infinite concept. Although I have given you some links, I'm going to prepare a short video about that to clarify the whole point, and I'm going to post this link just below this video. Anyway, so, well, of course, well, as you can see, this, for instance, takes a finite only 4 distinct values. Therefore, this is a discrete random variable. Here, for this case, again, this is a discrete random variable. What else may be this discrete? Actually, all the examples that we are going to be solving or talking about within chapter 3 is going to be discrete random variables. For instance, a typical example, which we are going to name as Poisson process, probably in the next lecture we are going to talk about that, is the number of phone calls. Let's say that you are at a station, this is your table, and there is a phone here, right? If this is actually supposed to be a phone, and you are waiting for these phone calls to that station, and you are answering those phone calls. So the number of phone calls within, let's say, a day is going to be actually a countably infinite random variable. Why? Because this value, the number of phone calls in a day, may start from 0 call. Actually, it's going to be, it cannot be negative. It can be 1, 2, and you cannot set an upper limit. Of course, there's physical, realistically, if you are talking about empirically, of course, there's an upper limit. But actually, from a theoretical or from a mathematical point of view, there is no upper limit for the number of phone calls. And this is going to be an countably infinite series. Therefore, this is going to be a discrete random variable. All right. Now, actually, what we have done is we have converted the concept of sample space and also event space into a random variable. So yeah, sample space and event space, a certain subset of the sample space that we are interested in, we can give any definition to them, right? But when it comes to random variable, we give each of these outcomes a specific real value. Now the next step to complete the whole probabilistic picture is to assign the probability. Now what we are going to do is we are going to assign a probability to each of these random variable specific values. Previously we did it for each outcome for the random experiment, each outcome of the sample space and event space. Now this time, since we are now in the random variable space, is going to be, are going to assign probability to each of these values. And so each probability value assigned to each of these random variable values is called actually a probability distribution. Within the scope of this chapter, we are going to be only concentrating on discrete random variables. Therefore, there's for each discrete for each value that discrete random variable takes, there's going to be a corresponding probability value, and this is going to be probability x at x. As you can see, we have a lowercase x here. It means the random variable, a capital X, the event that we are talking about, or the mapping we employed on the event or the sample space we are talking about, takes that specific lowercase x value. For instance, when we are talking about tossing a coin, for instance, I said a single coin again. The important point is how many times we toss it. That's an important thing. The sample space is heads and tails. Then the random variable representation is going to be anything that you like. As I said, 0 and 1 maybe. So heads is going to be 0, tails is going to be 1, let's say. And then the next thing that we should do is we should assign to each of these random variable values a probability. And when it comes to that, of course, we need some empirical tools. Up to this point, this is totally mathematics. But when we are talking about probability, there should be an empirical content to that, because Kolmogorov's axiom says nothing about how to assign probabilities to events, as I said previously, and we had different interpretations. So thinking about the classical view, the number of outcomes is 2. Therefore, the probability that x is going to be equal to 0 is going to be equal to 1 over 2, because we had 2 outcomes, and the one that we are interested in is in this single one, and probability x is equal to 1 is equal to 1 over 2. And from a frequentist point of view, this is going to be applicable if the coin is fair. But if the weight distribution is not uniform and there is something tricky about the coin, of course, these may not be the probabilities. But as I said previously a couple of times, it depends on how you define probability, and this is an empirical concept. Anyway, now when it comes to discrete random variables, probability distribution takes the specific name probability mass function. So probability distribution of a random variable x is irrespective whether it is discrete or continuous. It's the general name given to that. When we are talking about a discrete random variable, we may talk about its probability mass function, and probability mass function is going to be the probability value taken by that random variable at a specific x value. When it comes to continuous variables that we're going to talk about in the next series of lectures, this probability mass function, this word mass, will turn into density. And we are going to see that single points will not have any probabilities. That's an important, well, actually it may be a little bit complicated if you go into details, but we are not going to go into that much detail. There's going to be such a distinction between discrete and continuous random variables. Now we are talking about the easier one, discrete random variables. Let's continue. So probability mass function is the primary means of defining discrete probability distributions denoted by fx. So this is the usual description is something like this. This is probability mass function of random variable s x at a specific value of x. So this is the name of the random variable, and this is a specific value taken by the random variable. But usually, especially in your textbook, this capital X is actually omitted, and this is the form which is used. As you can see, this is a lowercase x. So actually, what is the meaning of probability mass function? As I tried to say, for discrete random variables, it's very specific. F at x is equal to whatever the probability value of that random variable at that specific value. It's very simple. And since we are talking about probability, it's going to, all of the rules related with probability should hold. The probability here should be a non-negative value at any x value, right? So the probability mass function is going to take non-negative values for all x values, all possible values of x, which should make sense due to Kolmogorov's axioms. And also, if we sum over all x values, the summation should be equal to 1. And this actually corresponds to probability of sample space is equal to 1. Because actually, over all possible x values, small x values I'm talking about, that the capital X can take, actually will cover the whole sample space. Therefore, that probability is going to be equal to 1. Again, let's talk about the case of tossing the coin once. So now again, the sample space is at tails, and x will correspond to 0 and 1. Then the probability mass function. which means probability of x at when it's equal to 0. If you like, here you can write x or not. Let me write for the time being. So probability of x is equal to 0. Let's denote it by 0.5. But as I said, these may be different values. These are related with in the empirical knowledge of the system. Now let's see whether this suggestion is consistent with the previous properties of the probability mass function. So actually, well, first of all the values of f, these are already, step 1 is already used to define the probabilities. All of the probability mass function, both of them are greater than 0, right? Greater or equals 0, and the summation should be equal to 1. Because these are all the possible values, because the random variable may take, because this is derived from a sample space. Therefore, when you add them, the result is going to be 1. So therefore, the properties of the probability mass function is satisfied. This seems very easy probably, but I think these are required to understand the idea from the basics. So what we usually do is, instead of showing, well, we can show the probability mass function in this form, but we prefer to show it in this form. We show the values of the random variable on x-axis and the probability mass function on y-axis, and we write the outcomes, the values that the random variable may take, and for each one we show the probability mass function with a vertical line such as this one, and we usually write the value of the probability mass function at these values. So we have 0.5 probability here. Now if we toss the coin twice, for instance, then note that the sample space, as I said previously, would be HT, HH, TH, and what else? TT. Then X would have been equal to 1, 2, and 3, and 4, let's say. Then each of these events will have a probability of 0.25. How do I obtain that? For instance, F1 is going to be equal to probability of that the event is H and tails, right? And this is actually equal to probability of H and probability of tails. And how do I obtain that? This actually comes from the independence property of tossing coins, right? There's a union of two events, but these two events are independent from each other. And since we assign 0.5 to each of these events, the probability is going to be 0.25. And you do this for all f values. Therefore, the resulting probability mass function is going to be 1, 2, 3, and 4, and each with 0.25 probability. And all these values are also 0.25. And for if the question were tossing a coin twice, then that would be the probability mass function. Now, the second description of probability is using a cumulative distribution function. And well, it's very easy. Well, first of all, how is this denoted? The lowercase f is changed to a capital F. So we are talking about fx here, shown like this. So the random variable fx and the value that the random variable takes. But usually this capital X is denoted if we are talking about a single random variable, and this is the usual way of showing the cumulative distribution function. Anyway, now the definition is very straightforward. It is, as the name suggests, you sum all the probability values up to and including X. So what you are interested, the definition is actually, when you write it that way, probability distribution function of X is, what is the probability of X being equal to or smaller than X? And this actually corresponds to this formulation. Oops. Why this formulation? Because this says probability of X values smaller and equal to X. Therefore, you sum all the probability mass function values smaller and equal to the xi value that you are interested in. I'm sorry, that the x value that you are interested in. So this x value here is this one. We are asked this one. So for all xi values smaller than x, you sum the probability mass function values. Now the resulting value still is going to be between 0 and 1. That may seem misleading at first or surprising at first, but it's not, please, because realize that this is still a probability measure, or actually this is still a probability. Why? As you can see here, this is not the probability maybe of a single point, but still probability of a couple of points. This may be also a single point, but still the probability of a couple of points is probability. Therefore, it should obey the rule that it should be smaller than 1. And this is also very simple. Since we add these x values on top of each other in cumulative fashion, if x is smaller than y or smaller or equal than y, then this cumulative distribution function of x should be smaller or equal than y. It cannot be greater than y, because we add these probability values on top of each other while we increase the x values. So let me show this on an example. The idea is actually very simple. Tossing a coin. This time I'm going to just omit the sample space. X is equal to 1, then 0 is 0.5, f1 is 0.5. These are, as I said, the probability mass function values. Now, corresponding to those probability mass function values, we are going to have probability cumulative distribution function values. So f at 0, for instance, is going to be equal to all x values smaller equal than 0. So therefore, this is going to be x smaller equals 0. Since we have only 0 which satisfies this condition here, because if you write 1, it's not equals smaller than 0. Therefore, this is going to be 0.1. And f at 1 is going to be equal to probability of. Therefore, this is going to be probability of x1 plus, probability of x1 plus probability of x0, which is actually mass function at 1 and mass function at 0, and therefore this is going to be equal to 1, which makes pretty much nice sense. Now, the graphical representation of probability cumulative distribution function is a little bit tricky. Nothing new under the sun, but you should be careful about how to draw this figure. Now, this is capital X probability distribution function. Now, here is the idea. We are at 0 here and we are at 1 here. Now, we might, oh, let me go back here. Now, actually, here, this diagram says that anywhere except this point here, 0 and 1, we have 0 probability mass function. Actually, you should think about this diagram here. Everywhere else, this probability mass function is equal to 0. Only at these 2 points, we have 2 spikes. So we should use the same logic here. We should be able to ask, so if, let me go back again. If you ask a question like, what is the probability mass function at 0.5, this is going to be equal to 0. Now we should be able to ask the same question here for probability distribution function, cumulative distribution function, I'm sorry. Therefore, we might be asking again questions like, what is the, let me ask this question, let me write the questions. For instance, what is this value? Cumulative distribution function value at point -5. It's going to be 0, because actually this means probability of x smaller than point -5, and there is no x value which is smaller than point -5. And if you do that up until 0 value here, it's going to be all 0. So this is like, okay, let me shade it like that. So this is all 0 here. But now if you ask this question, what is the cumulative distribution function at 0.5? Note that this is different from this previous example. This just asks what is the probability mass function exactly at 0.5. There is no mass here, probability here. On the other hand, this asks what is the probability mass function at 0 smaller than that value, which means this is actually asking this question. And hence, this is going to be equal to 0.5. So this might be the confusing point here. So what we do here, when we are exactly at 0, we jump to 0.5 cumulative distribution function value, and up to 0 we have 0.5 cumulative distribution function, because if you just go back here, F19 here, still this is going to be equal to 0.5 as long as we do not include 1 here. And once we include 1 here, we jump to 1, and then this is going to go to, for the rest of the x goes to infinity, this is going to be still 1. Why? Because when you, for instance, write f1.8, this is going to be probability x smaller than 1.8, and this is going to mean that probability of x1 plus probability of x0, which is going to be equal to 1. So this is how we plot a probability cumulative distribution function. As I said, it may be a little bit tricky. Okay, now a simple example. Let's say that we have we would like to find the probability mass function and cumulative distribution function of the given process. We have 850 manufactured parts, and we know that 50 of these parts are faulty. And we randomly select 2 parts out of these 850. We put all of these parts in a container and we randomly select without replacement. And if X is the total number of faulty parts that are selected, we would like to find the probability distribution and the cumulative distribution. And probability distribution function for the discrete case is, since it's shown the probability mass function, it is probability mass function. Okay, let's see. Now let's start first, try to understand this question. Let's first see, if we were to take a single part, what would be the sample space? Now, if we were to take a single part, the sample space would be a faulty, and the other one, let's call it what? The other one, faulty and good working, and call it non-faulty. Faulty and non-faulty. However, this is not the experiment because we select 2 of them. So therefore, this looks like at first sight faulty, non-faulty, and faulty, faulty, and we had non-faulty, faulty, and non-faulty, non-faulty. This seems to be the sample space, but actually this is not exactly the sample space of this specific experiment, because this specific experiment does not care about which one is faulty or which one is non-faulty. What it cares about is the total number of faulty parts. So let's directly define the random variable here. For this, for instance, outcome, what would be the total number of faulty parts? That would be 1 here. I am very sorry, I'm still not very good with this pen. Faulty, non-faulty, 1 faulty part. Faulty, faulty, 2 parts, and it sounds very interesting. Non-faulty, faulty, again 1 outcome, 1 faulty outcome, and non-faulty, non-faulty, 0 faulty outcome. Therefore, the random variable for this specific example can take values 0, 1, and 2. So this is the very first thing that you should do for to analyze a probabilistic example or probabilistic system. First, find the domain of X, find the support of X, the values of X which are going to take non-zero values. So these are the values that X can take. Note that it cannot take value of 3 because we only take 2 parts. We only pick 2 parts. Now, once we do that, we are going to, and note that now, this is going to be a discrete random variable. Why? Because we have finite number of outcomes here. Finite number of values that X can take. And now the next thing that we are going to do is, once we define the random variable and the values that the random variable can take, we are going to assign probability here. So fx is going to be consisting of f at 0, f at 1, and f at 2. We are going to find the probability mass function values at these specific x values. And now, assuming that using the classical view that each of these peaks out of 850 has equal likeliness of being picked, we are going to do the calculations. So what we are going to do is we are going to think about is as all right, I'm going to write the total number of outcomes here, right? So think about the sample space, and I'm going to write the size of the event space here. So the total number of outcomes, since I select 2 parts, we don't care about the ordering of the 2 parts. We only care about whether one is faulty or not. Therefore, the number of different outcomes would be 850 choose 2. We are going to use permutation. We select 2 parts out of 850. So this is going to be size of sample space. All the possibilities. The ones that we are interested in is x is equal to 0, 0 faulty one. So all the 2 would be from the non-faulty. And since the non-faulty is 800, we are going to choose 2 from this 800. And note that this is going to be the size of the event space. And here event is x is equal to 2. And correspondingly to this one, here this is going to correspond to this event. Non-faulty, non-faulty. So as you can see, actually I have come back to here this sample space, although it doesn't exactly correspond to this experiment, because this experiment is only interested in total number of faulty parts. In order to assign probability, I use this sample space and the classical view of equal likeliness to come up with the probability. So when you do the calculation, the result is 886. And for one faulty parts, again the sample, say this one is going to be in the denominator because this is size of the sample space. Now we are going to be interested in single faulty part, which corresponds to this one and this one. Now this means that we are going to be taking one element from the faulty 50 of these faulty parts and one element from 800 non-faulty parts. Therefore, this part is going to be, I have to erase this part, right? Otherwise, it's going to be too messy. Okay, you may say, where does this formulation come from? Actually, I used here multiplication rule. We have a 2-step procedure. In the first step, we select either the faulty one or non-faulty one. It doesn't matter, but from 801, we choose from 800 different options, let's say, we choose one of the non-faulty ones. And then in the next step, among the 50 of the faulty ones, we choose another one. That's why we multiply these two. And when you do that, so as you can see, I always try to verify what I do using the theorems or using the axioms that we have covered previously. So this is the second probability mass function value. And the last one, F2 is going to be equal to this. I'm going to be a little fast. Choose 50 choose 2 because actually all the 2 will be, both of them will be faulty. Therefore, it's going to be chosen among 50 parts. And again, this part, the denominator is again the same, 0.003. All right, now let's finish the question. Okay, so these are the probability mass function values shown algebraically. Now let's show them. I'm going to erase this part. The nice thing about these videos is you can stop there, right? Unless being in a class, if I were to erase this during a lecture, it wouldn't be, of course, nice. What I'm going to do is I'm going to write these values on a graph. Let's see, we have X here, we have probability mass function here, and we have the outcomes are 0 and 1 and 2. And the first one is going to be like 0.886. The second one is somewhere here. Of course, the scaling is awful, but yeah, I'm sure you can make it better. All right, so this one is 0.003. So when you look at this figure, you can easily see that the number of faulty parts has a very high probability of being 0, or at most maybe 2. I'm sorry, 1, but it's a very low probability that there are going to be 2 faulty parts. So let's now solve the second part of the question. What about the cumulative distribution function? So cumulative distribution function, f at 0 is going to be equal to 0.886. F at 1 is going to be equal to the addition of these two values, 0.886 plus 0.111, and another one here, and the result is 0.997, and F2 is going to be equal to 1, because actually it's going to cover all the possibilities. So, oh, I can do this better, I guess. And we have 0 and 1 and 2, X and capital X. This time we have here up to this point 0. Then here we have 0.886, starting from here to here. And then we have here 997, starting from here to here. And then finally we have 1 here, which is going to start at 2 and go to infinity. And this is going to be our probability distribution, cumulative probability distribution function. How to read this? For instance, a value here, what's the probability that the resulting X is going to be smaller than this value, greater than X, is going to be probability of 1. That's how we can read this. Okay, the next thing that we are going to talk about is the expected value of a discrete random variable. Now, we have defined probability distributions of discrete random variables, but the continuous one is going to be just similar to that one. So once we have the probability distributions, we may describe probability distributions, probability mass functions, by some easier to understand statistics, or easier to understand, let me say, mathematical functions. We are not into statistics yet. So what do I mean by that? For instance, we have a probability mass function here. We may represent this probability mass function, not all the properties of the probability mass function, of course, the whole information will be given by the probability mass function, but we may represent the location of this probability distribution function, probability mass function, using the expected value. And when I say location, this should give you an alert from the very first chapter that we have talked about descriptive statistics, which is not the very serious statistics that we have talked about, where we had samples and we tried to describe the samples and we use the concept of sample mean. This is very similar to that sample mean concept. Actually, the same symbol is going to be used for the concept of population mean. Later we are going to talk about when we come to populations in chapter 7. So now, to describe a population, to describe a probability distribution in a simpler way, expected value formulation may be used. So we either show it with this one or we represent it as mu. The formulation is identical to finding the center of mass of an object. What do I mean by that? These X is our random variable, the values that the random variable can take. In physics or in mechanics, this corresponds to the location where mass is accumulated. And in physics, we use, instead of mass, instead of Fx, we use the corresponding mass at that point. And when it turns to probability, we use the probability mass function. And note that this probability mass function is between 0 and 1. Hence, what we are doing here right now, we have different at x values, we have different probability mass functions. We weight each of these x values using the corresponding probability mass function. And since these are between 0 and 1, this is basically taking the weighted average of these values where we have some non-zero probabilities associated at these points. Therefore, for instance, when we find the expected value, we're going to find the expected value somewhere here, which is going to be, as I said, the center of mass of the system. If you take this probability mass as the actual mass of the suspended from each of these points. Note that just like the one that we have covered in the first series of lectures for samples, just like sample mean is not the typical value of a sample, expected value will not be the typical value of a distribution. Here, for instance, actually our distribution can take only these 5 different x values, right? For the rest of the values, there is 0 probability of x taking that value, yet the expected value will be somewhere here corresponding to a point representative of the location of the whole distribution. For instance, for the previous example, what's the expected value of the faulty parts? When we ask this question, and for the previous example, I'm talking about this one, we are going to be finding the probability, the expected value using this representation. In this probability mass function, where is going to be the expected value? Well, actually, we can directly use the formulation that is shown above. Fx is equal to each x value multiplied by the corresponding probability mass function. And here, x values will be equal to 0, 1, and 2, right? From this set, we are going to, because we can't only have these 3 non-zero values. So we are going to multiply with these, let's call them xi with the corresponding probability mass function values and find the result. So it's going to be 0, the first x value, multiplied by the corresponding probability mass function value, which is, I guess, 0.886, plus 1, the second x value, the non-zero, the x value with non-zero probability, is going to be multiplied by its corresponding probability mass function value, which is this one, plus 2. There may be 2 faulty products if you recall. It's going to be 0.003. And when we add these values, we find the value of 0.117. Now, if we go back to this figure, 0.117 is going to be here. Let me show it again because it's a little bit confusing maybe. Okay, it's going to be point somewhere here between 0 and 1, but very close to 0. As you can see, actually, the x can never take a value, excuse me, of 0.117. Yet, this is a very good representation of the location of this distribution. Note that the similarity to the samples that we have covered in the very first chapter is not only confined to sample mean and the expected value, also the probability mass function. You should have realized, or maybe you should at least realize at this point, that this very much looks like an histogram. So maybe you can associate everything that we have done in chapter 1, statistics related to samples, with actually finite samples that we were talking about. Now we are talking about the mathematics of the whole distributions, but surely they are going to meet somewhere in the middle that we are going to, I hope, cover starting from chapter 7. Okay, now the second mathematical function that is used to describe distributions, in addition to expected value, is the variance and standard deviation of a discrete random variable. Just like the relation between the expected value and sample mean, where sample mean belongs to a sample or describes a sample, whereas expected value with a similar formulation describes the location of a distribution. The same analogy is between sample variance, which describes the spread of a sample, with the variance and or standard deviation, which describes the spread of a distribution. So note that again, this, we are not talking about a single sample here, but let's say about all the potential samples from a discrete distribution. Anyway, now the discrete random variable variance is shown with a sigma square, right? It's shown with V variance X. So this whole thing is a bit important here. E here is called the expectation operator. So I'm going to be talking about this expectation and variance and these curly brackets and X as an operator on X. So I'm going to be talking about this as the expectation operator. This operator is going to operate on some random variable, X, Y, whatever. So a similar case here is also seen. Here we have variance operator acting on X. So this is going to be called variance, or it's going to be shown with sigma square. Now, what is this equal to? Here, this is the formulation, but this formulation needs some explaining. This is actually equal to, so variance operator can be converted into an expectation operator. How? This is basically equal to X minus expectation operator X square. Now, actually, let me also show it that way, or this way. This representation may seem better at first sight, right? But usually statisticians get rid of these parentheses, and what they do is they put the square here. So what they mean is, or the way that this operation is computed is X minus X square, then take the square, and then at last expectation operator is employed. So the order of the operations is first the subtraction, which is obvious. Now the important point, not first the expectation operator, then the square, it's vice versa. So there is a somewhat like a hidden parenthesis like this, but usually this is not shown. Therefore, please read it that way. So first take the square, then take the expectation operator. So that's all with the order of operations. Because now we have just like the four operations, addition, multiplication, and subtraction, division, we have actually a fifth one, which is expectation operation. So you may think about that way. So what does that mean? Now this is a little bit more confusing than just expectation of X. This was a kind of a representation of the location of the distribution. What about this one? Expected value, what you expect this difference square to be. What do I mean by that? This is again the expected value of X, which is the center of mass. Any X value, the deviation from this value. Note that that may seem interesting, but if you do this, this is going to be equal to 0. I'm going to come to how to deal with these expectation operator, the algebra related with these operations, but just use your logic. What do you expect the deviation of a random variable from the expected value? Actually, this is equal to be 0 without any operation. Just use your logic, because expected value is defined by that way. Find a point such that it balances all of the rest of the points, such that deviation of that point, the expected deviation from that point, is going to be 0. So why is not this equal to be 0, but it's variance? Because we have a square term here. So once we find the deviation, we don't find the expected value, but we square it. When you square it, again go back to the derivation or interpretation of variance and standard deviation in the first lecture. Remember, we had positive and we had negative deviations. When you sum those two directly, they are going to cancel each other. But when you have positive and negative deviations, and when you square them, this elongates, and this one also in positive direction is going to elongate. So therefore the result is not is going to be non-zero, or I'm sorry, non-negative. It may be 0 or greater than 0. So that's why this operation x minus mu square expected value. So what do you expect your squared deviation from the center of mass to be equal to? Is going to be a measure of spread, or the variation of the distribution, or here it says proportion of the scatter in x. All right, so as standard deviation is just the square root of that value. Now let's continue from the previous example. If we continue from the previous example, what is going to be the variance equal to? Now variance is going to be equal to, using the very same formulation. Now we are going to be, since this is expected value, this can be written in this fashion. Actually, I'm going to show it in a couple of minutes why this is so. So whatever you write here, this can be directly written here, but what we are going to multiply with is the probability mass function. There's not going to be a square or something like this. So what we are going to do here is x is going to be equal to 0, 1, 2. It can take 3 elements, 3 outcomes. So xi is going to be subtracted from the expected value. This time let me use mu for expected value. We square and we multiply by xi. So therefore it's going to be equal to, the outcomes are 0 minus 0, 1, 1, 7 square. This one is the expected value, or mu, which we have calculated previously, multiplied by 866 plus 1 minus 0, 0, 7, 0, 1, 7 multiplied by 1, 1, 1. And the last term is 2 minus 1, 1, 7 multiplied by 0, 0, 3. And the result is going to be equal to And as if you recall from the first lecture, usually variance does not give a very clear picture of the spread of data because the unit is squared with respect to our original data. So when we find the square root of that variance is going to be equal to the standard deviation, which is going to be 0.331. Now this gives a nice summary of distribution. If we go back, the mean of this distribution is 117, and the standard deviation of this distribution is 0.331. Of course, note that these two functions, mu and the values these functions take, do not still capture the whole distribution. This is the full information. At 0, we have this much probability. At 1, we have this much probability. At 2, we have this much probability. On the other hand, this gives a nice summary of that distribution. The location is somewhere here, and the standard deviation is, or the width of the data is 0.3. Note that actually it does not include, if you add mu to one, I'm sorry, this should be sigma. 1 sigma value, you are still not going to be able to reach 1, or of course 2, yet still this gives a good idea about the total probability, how that total probability is distributed with respect to different values of the random taken by the random variable. All right. Now, a little bit of mathematics related to mean and variance of linear functions. Now, let's say that you have a function like this. You have a random variable, but what you are interested in is a random variable, another random variable such as this one. Well, the very typical example that we are going to see might be, for instance, let's say this, let's go back to the previous example, that the number of manufactured parts and faulty parts. Now the faulty parts may be 0, 1, and 2. And let's say that you are going to sell these parts And if you, when you sell these parts, for instance, if you sell these two parts that do not have any faulty parts among them, you are going to get that much amount of money. And if you sell these two parts with a single faulty one, you are going to get that much amount of money with different amounts of monies. And if you are going to sell two faulty parts, you are going to get the least amount of money. Therefore, and you can, let's say that we just define a deterministic function between x and y in terms of a and b. So this is a deterministic function. What do I mean by that? Once you know the number of faulty parts, you can find the profit that you are going to make. That's fine. However, x is itself a random variable. Since x is itself a random variable, y also turns into a random variable. Now, y is a deterministic variable only after x is known. That's why I call this a deterministic function. However, x is a random variable. Therefore, y also turns into a random variable. Now, the question may be, what is my expected gain at the end of this process? Therefore, since I can find a functional relation between x and y in this manner, I can easily replace x by y in this formulation, ax plus 1. And note that I repeat again, a and b are constants. They are not probabilistic variables. In this case, there is actually a very short proof here, but let me go over that because it's important. Now, we are going to write this here, expected value, and multiply by the corresponding probability mass function. Now, I said that in the previous slide, I haven't gone into that, but whatever quantity we would like to find the expected value of, you can write it here, and you are going to write the corresponding probability mass function for the random variable. That's an important thing. We have actually employed this rule here. Note that I have written x minus mu square, and here the random variable is x. Therefore, I'll multiply it by the probability mass function of x. That's the important thing. There was no square or something like that here. There is no complication related to mu or things like that. Only the random variables probability mass function. Since a and b are not random variables, since x is the only random variable, we are going to be multiplying by probability mass function of x. Yeah. Then what we do is simply you can, since this said summation operation, you can actually write two different terms, ax times fx plus b times fx. Note that b is a constant, so you can take b out here. And note that probability mass function summed over all the support of x, which support means all the non-zero, the x values with non-zero probability is going to be equal to 1. Therefore, this is going to be equal to b. And here a is a constant. You take it out. X times fx is already expected value of x. Therefore, we can write this very nice relation, which is already framed, but now it's double framed. Now, actually, once we see that, we can understand now the properties of expectation operator. Expectation operator, when applied on a linear function of the random variable x, can be turned into b outside and a here outside. Now, what do I mean by linear operator? If there were here an x square, right? Or it, let me put it that way, square like this. Could we have done the same thing? No, actually it comes from this. Then we would have a square here. When we have a square here, we won't be able to do this dividing into or separating into two terms operation. Now the same thing or a similar approach can be employed on variance operator. Now for variance operator, note that this is actually equal to expected value of ax plus 1 minus expected value of ax plus 1. Now that may seem a little bit confusing, but this is exactly what we are trying to find by writing this. Now, is there an easier way to handle this? First, actually, what you do is you should go through these steps. So I said C problem 374 here. And when you do all of these, you end up with this equation. Now, that may seem a little bit intuitive, whereas this one seems a little bit strange probably at first sight, because B has disappeared. That constant has disappeared. And we have A square here. And that may seem, as I said, a little bit interesting, but let's go over this once more, this time from a little of a distance, and see what's going on. Now, let me go about, again, related with this example. Let's say these are the number of losses. So what did I call it? The number of, I'm sorry, not loss, but the faulty products. And let's say that the amount of money that I'm going to be making is 1,000 units minus, so B is going to be 1,000 times 400 times X. These should be capital, I'm sorry, because we are talking about random variables here. This is going to be the deterministic relation. So if there are no faulty products, I'm going to be winning 1,000 units of money. If I have one faulty product, the money is going to be 600. If two faulty products, then it's going to be 200. The money is going to be even less. I should be thankful that I even win that much money, even if I sell two faulty products. Anyway, now the question is, I'm interested in expected value of how much money am I going to make? Expected value of Y. Now this simply says that this is going to be equal to 1,000 minus 400 expected value of X. Now this makes pretty much sense, because actually you just forget about these values. You multiply this, just like directly multiplying here whatever the X for X value given, whatever the money that I'm going to make, I can find. It's going to be the same algebra is employed for the expected value. So the expected value is, if I recall, 0.117, was something like that. It was the expected value, or what was the expected value of X? Let's see. Yeah, 17. That was the expected value. So what I do here, I put that value here, and it's going to be 117 times 4. What's that going to be? It's about, let's say, I don't know the exact value. If this is the, oh, is it wrong? Yeah, this is 45, I guess. Something like this. So it's going to be 955. So this is the expected money that I'm going to be making. Now, variance of Y. Here is the interesting point. Variance of Y is going to be directly equal to variance of this value 400x. This time, I don't care about this value, because what this 1,000 does is it's a constant. It just changes the location. The variance of X, the change in X, only affects or reveals itself when multiplied by 400 and turns into a variance in Y. Since that 1,000 is a constant value, it does not show itself in variation. So this is going to be simply equal to 4,000 square variance, or 400 square, I'm sorry, variance of X. And this is going to be, actually just go back and do the calculation. And then when you take the square root, actually, I think this is going to be much more interesting. The variance of the standard deviation of Y is going to be equal to 400 times standard deviation of X. And what did I find standard deviation of X? Let's finish the question. 0.331. So it's going to be this value. So it's going to be 33 times. It's going to be something like 120, something like this. So the money that I'm expected to make is 955, and the standard deviation is 120. Anyway, so that's how you can apply these rules. But again, note that we have to have linear functions of random variables. Non-linear functions cannot be directly put into this form. One interesting point, and I expect you to prove this on your own, that may seem counterintuitive, but also sigma square, which is variance, is expected x minus mu square is equal to this quantity is also equal to this. And if you again recall, in sample variance, a very similar formulation existed. So what you should do is actually put this form into this formulation and see that the same formulation maybe is going to be obtained. So to find the variance of a distribution, instead of using x minus mu square and multiply by fx and add all of these, you can first take the square of all non-zero probability x values and multiply by the corresponding mass functions, add them together, and then subtract from mu square.